Okay, we've been computing Hilbert series. So last time I showed you that if you can find a free resolution for a module, that means that you're going to be able to compute its Hilbert series very easily. The problem is that you guys realize that finding a free resolution is not always so easy, right? So that was all banking on the hypothesis that you can do that, and maybe you don't know how to do that. I mean, we have a method for doing it, but maybe it's not practical. If you have a huge ideal, maybe it just becomes impractical. Maybe it's so big that a computer can't handle it. So I want to start by showing you another way of computing Hilbert series, which is extremely useful. And it goes like this. So this is a very nice theorem due to Macaulay. So let's say that we have a finitely generated module P over R, where R is our polynomial ring. And one thing we can do is write it in this way. We can always write it as the free module mod by a module of syzygies. So because it's finally generated, you can say, okay, well, if I have 3 generators, let me take the free module on 3 guys, and then mod out by the relations they satisfy. And then you will get something that is isomorphic to P. You can always do this in practice. So I'll write that here. So F is the free module with a homogeneous basis and M is the submodule of relations. We'll do an example in a second. Then the Hilbert changing my notation. The Hilbert either function or series of this guy that you're trying to compute is equal to the Hilbert series of the analogous guy, where you go to the initial module with respect to a certain order that you like. So this is the statement, and what I want to do is first show you how you use this in a computation. And that way I think you'll understand better what I'm trying to prove, and then we'll prove it. Okay? So let's start with a random ideal. So I don't know. What's a random ideal, Laura? We didn't stage this ahead of time or anything. YZ. Z squared minus xz squared. Okay, that's an ideal in the polynomial ring in 3 variables. Okay, and let's say that I ask you to compute its Hilbert function or its Hilbert series. Okay, how are you going to do it? Well, you have several options, like finding a free resolution, But you can try to do it in this way. Okay. Now, there's one fact that is nice here, which is something that we proved last time, which is that, by the way, think about what it would mean to do this manually. If I asked you to find the polynomials of degree 4 here, you would have to figure out what are all the things that you can write as a combination of this guy of degree 2 and this guy of degree 3. And that'll be a mess because it's very hard to keep track of those things. There's going to be a lot of cancellation, possibly. This is not really reasonable to do by hand. Even if I ask you for degree 4, it's going to be very hard. You have to do it for every degree. So this is hard. So the first reduction that you can do, which is very nice, is that we proved something last time, which is that you can either compute the Hilbert series of the ideal or of the quotient. Right? We proved this, and the point is that this is very easy because this is just, in this case, we have 3 letters, so this is 1 over 1 minus x cubed. And so we can compute this. And the motivation for doing that is that I keeps increasing in every degree. R mod I is taking the big polynomial ring and modding out by a big ideal. And so hopefully this is smaller and we can control it. Okay. So that's the motivation for, instead of doing it for I, we're going to do it for R mod I. Okay. But another motivation is that I have this wonderful theorem of Macaulay now that tells me that if I want to compute the Hilbert series of R mod I, then I might as well make my life easy and just compute the same thing, but instead of doing it for I, I'll do it for the initial ideal with respect to some order that I like. Okay. And we'll see that this is easier. Okay. What is the initial ideal of I? Well, that depends on what order I choose, right? We need a term order to do this. And I know that by now you guys don't want to do this by hand, right? I already put you through that once, but I told you I would only put you through that once in life. So what do we do now? Well, now we let computers do it for us. So now you all have Mathematica on your computers right there. And so you just type in, what do you type in, Laura?
Groebner basis.
You type in Groebner basis. She's teaching me. Honestly, I'm embarrassed to say that. I've never used Mathematica, but. So x, and then you have to go like this, right? Y times z plus z squared. Okay, you get the point. And then
you put a comma and then you put the terms like the order you want them to have. But not like that. You just put curly brackets and comma.
Curly brackets, x, y, comma, z. So this will give you the lexicographic Groebner basis. Okay, wonderful. It's so easy, right? I mean, you should never do this by hand again, really. And of course, you could do this in Mathematica or in whatever program you prefer. You can do these things. So you do this and you get the answer. Wonderful. So what's the answer?
That's a Groebner.
No.
Oh, I could have given you another one. So you can.
No, I wanted to. We did stage this, but we staged it wrong. So
No,
because
you can change it. You can change the set.
We had this, right?
Yeah. X, Y, Z.
I didn't want to start with a Groebner basis. But then, so you guys know now what the computer is doing in the background, and out comes probably the reduced Groebner basis, what comes out, which is x cubed plus 1?
Minus XZ.
X cubed minus xz squared, and yz plus z squared. Okay? Wonderful. Now that's still the ideal, but this is a Groebner basis now. So this is a Groebner basis. By the way, I should let you know that sometimes people just spell it OE because this is I guess this is really said like Groebner. This is the O with, is that called an umlaut? Umlaut. And sometimes when people translate things in German that have umlaut, they'll put any instead of the umlaut because the keyboards don't have it so easily here. But anyway, so this is the Groebner basis. I spelled it like that. So what do you do? Well, now you take the initial terms. The initial term is here and here. Okay. So the initial ideal is x cubed and yz. Okay? And so now what we need to compute is this guy. Okay? But what are we doing? We're taking all the things that live, all the polynomials in 3 variables x, y, and z, and we're taking out multiples of yz, and we're taking out multiples of x cubed. Right? So that means that manually we can now write out a basis for the things that don't get killed, either by x cubed or by yz. So what's a basis for this guy? So think about it. Think about all the monomials that are not 0 in that ring. It's easy. You can do it. What are the ones of degree 0? Well, 1 is the only one of degree 0. The ones of degree 1 are x, comma, y, comma, z, and none of those gets sent to 0 in this ring. What about the ones of degree 2? Well, first of all, you have x squared, y squared, z squared, and then you have xy, xz, yz. But you see, yz is equal to 0 in this ring, and so that means that I don't need it. I throw it out. Not only do I not need it, I can't have it there, right? Because this is supposed to be a basis. Now, for the next degree, well, what are the things that are not a multiple of x cubed and are not a multiple of yz? 1 cubed. Let's just do it in order. So out of the x cubed, y cubed, z cubed, these guys survive. Then out of the x squared y and all those things, all of that survives. X squared y, x squared z, xy squared, xz squared, and I think that's it, right? Okay. Now what about degree 4? Things that are not a multiple of x cubed and are not a multiple of yz. Kind of wish we had picked a smaller example, but well. Should we do this? Let's do it. We started something, we should finish it. So what do we get here? X to the 4? No, not x to the 4th. By the way, I mean, I should tell you that there is a nice graphical way of seeing this. Okay. Which is that, let's put a point for each one of these things that we have here. Okay, so x cubed, it lives over here. This is supposed to be the positive or octant. So this is where x cubed lives, and this is where yz lives. Okay. So what are the multiples of x cubed? This is going to be a challenge to draw it, but I'm going to try anyway. So the multiples of x cubed are basically the things that live above x cubed, right? So it's all this stuff that lives from x cubed forward. Yeah. And what are the multiples of yz? These are the things that, starting at yz, I'm going to move the x-axis. It's getting in my way. Doesn't help much, huh? Send her over here. Help a little bit. It's hard to make it help it. Okay. And so really, you're imagining that there's kind of a big purple cone coming out, a big brown cone coming out, and those are the things that are multiples of x cubed and of yz. Or of yz. And so the things that we're trying to get are the things that are not a multiple of either. Can you see what those are? It's basically all of these guys. There's a little corridor here. This is hard to see, but this whole corridor works, right? And then this corridor, I guess. That's it, right? And that's my basis. So I actually wanted to stage it a little bit better with Laura, because a minute before walking in here, I just said, hey, give me a homogeneous ideal. Now, generally, when you do this, an example that I wanted to do, I didn't want this basis to be infinite. In this case, it happens to be infinite, right? But at least that means at least we can write very explicitly what the generators are, and that means that we can write the Hilbert function explicitly and then carry out this computation. Okay. But I guess the point that I would make is that computing the growth of R mod I for an arbitrary ideal is very difficult, because it's very hard to see anything, and you can't keep track of the cancellation or anything. But by going to the initial ideal, then all of a sudden it becomes a combinatorial problem of just enumerating points and counting. That's what this theorem is going to allow us to do. So now you see how you're going to. Now you see one way of solving problem number 5 in the homework, by the way. Okay. So let's prove the theorem then. Let's prove the theorem. So proof, I'm going to do the following. I'm going to prove something similar to what I'm saying there. That's why I wanted to carry out this example. Let B be the set of monomials in F which are not in the submodules generated by the initial terms of M. So here you're thinking that M is what over there is I, right? So what I did is basically the initial monomial, the initial module of M is what I computed here to to be the initial ideal I. Right? So I started with, this is my M in this proof, and this is my initial ideal M. Okay? And I'm defining B to be the monomials in F which are not in, I'm missing an in. In. Okay. So do you guys see why this set B that I'm defining is exactly the set of dots in this picture? This right here is B. All these black dots. Okay. They are the monomials which here correspond to dots, which are not in the initial module, which is the purple stuff and the brown stuff. And my claim is that B is a basis for F mod M. You see, you have to be a little bit careful because these things that in B live inside F, and I'm claiming them to be a basis for F mod M. So really, I need to take B bar to be their image in F mod M. Okay? So I'm claiming that B bar is a basis for F mod M, and that if I take those guys that have degree D, then this is going to be a basis for F mod M in degree D. Okay? That's what I'm saying. So what I'm saying is that these black dots over here, not only are there a basis for this guy, which I think is fairly clear, but they're also a basis for R mod I, which is maybe less clear. Okay. B is a basis for this guy, but also for this guy. That's what I'm claiming. Okay. And so you see that if I can prove this statement, then I'm going to be finished, because basically I've provided a basis that is a basis. I mean, this is a set of monomials such that when I consider them as elements of this ring, they're a basis. And when I consider them a basis of this ring, they're also a basis. And so that must mean that this guy and this guy have the same size. And the size is given by this set. Okay? So this is how I plan to prove this proposition. Okay? So now, what do I mean here when I say basis? I mean basis as a vector space, right? So as vector spaces over my field. Okay. So let's prove this claim. Are there any questions before I prove this claim?
So
yeah.
in our example, did we ever actually
No, so you didn't miss it. So, I mean, the thing is, like I said, I was hoping for the black points to be finite. And generally, when people actually, I mean, a lot of times when you actually want to compute this, you just get I thought we were going to get like 1 point in degree 0, 3 points in degree 1, etc. But, I mean, we can do it. How many points are there in degree 0? 1. Right? This is the only guy in degree 0. The guys in degree 1 are kind of the ones that are in the plane x plus y plus z equals 1. So there's 3 of them. Okay. So in the next guy, there's what? 5, because this guy fell out. So what is it? 1, 3, 5. That's it. How about for the next one? It's going to be 3 here and read here, 6. And then it's going to stay at 6. So actually, we can do it explicitly, even though it didn't come out to be finite. That's it. This is a basis for this guy, and that means that what's the Hilbert series of this guy? It's 1 plus 3x plus 5x squared plus 6 times x cubed, x to the 4th, etc. So this is just x cubed over 1 minus x. Okay. And that means that the Hilbert series that we wanted is 1 over 1 minus x cubed minus 1 minus 3x minus 5x minus 6x cubed over 1 minus x. So that's the formula, and this is kind of a medium-sized computation of this type. They tend to be either easier or sometimes they're very hard, actually. But anyway, so we can do it. By the way, so remember this issue about being eventually polynomial? Looking at this answer might give you a hint as to what this eventual thing might be about. There's some garbage here that maybe you didn't expect to see. So does that answer your question? Thanks for making me do that, actually, because it kind of ran away as if we couldn't do it, but we can do it. Okay? All right. So proof of claim. This claim is not very hard, actually. So we need to prove that it's a basis. So let's prove two things: linear independence and spanning, right? So linear independence. So let's suppose that we have a linear relation that looks like this. So some relation that looks like this. Let's say from I equals 1 to k, where m1 bar up to mk bar are inside b bar. Okay. So the linear relation between elements of b bar and these lambdas are supposed to be field elements. Okay. So we have a linear relation, and we would like to show that actually that must be the trivial relation. Okay. So how do we do that? Well, where does this equation live? This equation lives in f mod m, right? And so that means that we can lift it to an equation in f. What this is saying is basically that when I take the coset of this guy mod m, it's the zero coset. In other words, what it's saying is that when I take this is inside m, so that when I mod out by m, it becomes 0. Okay? So let's call this m. And this is in big M. Well, now look at this. Look at the term, initial term of m. Well, the initial term of m is inside the initial module of big M. But if you look at this, these are all monomials, right? By definition, the mi bars are in b bar, which means that the mi's are in b. So they're monomials multiplied by constants. So the initial term of a sum that looks like this must be one of the monomials in the sum. It couldn't be anything else. So the initial M must be one of these guys. Maybe with some coefficient, but that's it. Okay. And what I just showed is that Mi is in the initial module, but that's a contradiction because Mi is in B. And things that are in B are not supposed to be in the initial module. Okay. So that's that. That's the first half. So contradiction. And now for the other half, let's prove that these guys span. Okay. So let's suppose that they don't span. Let's suppose that there are elements in here that I cannot generate. So let's say that I take some element f bar, which is in f mod m, and I cannot generate it. It's not generated by this b bar. Okay. Well, what does that mean? That means that f is not generated by m and b. Because if f were generated by m and b, then when I take quotients by m, on this side I would get f bar, and here I would get b bar. So I would get a way of generating f bar by b bar. So f is not generated by m union b. Now there might be several choices for f that satisfy this. Let's take a minimal one. So take one such f. How do I choose what's minimal? Well, I have some freedom of how to do it, but I'm going to do it according to this initial order that I have here. Okay? With this monomial order that I have here. So I'm going to take such an f with the initial term of f minimum. Okay? So now I'm going to consider two cases. Either the initial term of f is in B or it's not in B. So first case, the initial term of f is in B. Then I'm going to do the following. I'm going to say, well, look at the term g, look at the polynomial f minus its initial term. Okay? This guy cannot be generated by M union B. And the reason for that is that if it were generated by M union B, then I could add the initial term of f to it, which is in B, and I would have generated f. So if I can't generate f, then I can't generate g either. Okay? So g is not generated by M union B. But you see the way that I obtained g was by chopping off its smallest term. Its biggest term, I'm sorry. And so that means that the initial term of g is less than the initial term of f. And that's the end of the story. That's a contradiction because I chose f to be minimal. So that settles that case. Now let's do the other case. So let's assume that this guy is not in B. Okay? And so then what does it mean to not be in B? Well, B consists of the monomials that are not in the initial module. So if you're a monomial and you're not here, it's because you are in the initial module. Okay. What does it mean to be in the initial module? It means that there exists a module element such that m is equal to the initial term of f plus big plus smaller things. Now, I also take f, which is also of this form. F is equal to the initial term of f plus smaller things. Okay. And I subtract these guys, and I get that f minus m is equal to something that consists of things that are smaller than the sum of terms which are smaller than the initial term of f. Okay? But now you see the same argument applies, that if I cannot generate f, then I cannot generate f minus m either, because if I had f minus m generated, then I would add m to it and generate f. So that means that this guy is not generated by m union b, but all of it is smaller than the initial term of f. But its initial term is smaller than the initial term of f. And so I get almost the same contradiction in a different way. Okay. So that's it. That finishes it. So you see, it's a theorem that the proof is not too hard, but it is an extremely useful theorem. You guys have any questions about what I did here? It's good. So what does this do? It basically tells us that if you want to compute the size of any module, any R module, then you just need to know how to compute the Hilbert, the function or series, the size of R mod I for I monomial. Computing mod n. R mod I. So you see, I mean, it's what it is. So if you want to compute any Hilbert series, you just need to know how to compute the ones for monomial ideals and then go from there. Okay. And what I'm claiming is that this is easier because this is, I mean, it depends on your point of view. This is for me, it's easier because it's combinatorial. Some people think that's harder. It's a matter of opinion. I should tell you that, I mean, for one thing, it is basically this idea of counting points, and it really amounts to that. Okay, so if you're happy counting points, that means that you're happy doing it. The problem is that if you have n variables, then you're counting points in n dimensions. Right? So very soon you can't really draw this anymore, but you can do it sometimes. But I should tell you that there are theorems that say that even though this is easier, it's still very hard. So if you guys know what this means, this is an NP-hard question. Okay, so that means that there is no good algorithm that can do this. A polynomial time algorithm that can do this. Given a polynomial ring, given a monomial ideal, use the Hilbert series, that's NP-hard. By the way, if you guys are interested in this kind of thing, that could be a nice topic for the project. Study why this is such a hard question. But well, what that means is that this is even harder, right? I mean, we reduced it to this, and okay, so this is hard, but this was harder. So that tells us that the original question was a difficult one, and the answer, it's difficult, but at least we have some tools to deal with it. I mean, I hope you agree that this is a difficult question. Given any modular over a polynomial ring, measure it. It's hard. And we reduce it to something that's hard. But we have tools to do this. We have a great tool to do this, which you have in the homework, and which you will prove in the homework. And let's see if, I mean, it's stated in the homework. Basically says, if you want to do this, there's kind of an inductive procedure where what you do is you take I, and you kind of split it into something I prime and something j, and basically you reduce the computation of this guy, the computation of this guy, and of this guy. So there is a recursive way of doing this, and it works, and you'll prove that. You'll prove that in your homework. So maybe I mean, one thing that you should observe in the homework is that if this ideal I has k generators, then these guys have k minus 1 generators each. So that means that they are smaller. So this really is a recursive process that terminates. But it's still recursive, and it still takes a while. But we're going to spend a while talking about this question of just computing these things from monomial ideals and developing some good tools for doing it. But the thing that I wanted to tell you is why Macaulay was interested in this. Because Macaulay had a very ambitious project in mind. And his project was basically this one. He wanted to answer the question, if I give you a sequence like 1, 3, 5, 6, 6, 6, 6, 6, does there exist a ring with that Hilbert series? So he wanted to characterize what Hilbert series looked like. And I don't know about you, but to me this sounds like a very ambitious question, and I would have been too scared to ask it, because I thought there's no way that I can answer this. It seems to me like a very hard question, but basically what he did here was saying, well, the Hilbert series of anything is the Hilbert series of something combinatorial, and now I can do combinatorics. Yeah. And then, so what he did is reducing, characterizing the Hilbert series of anything to characterizing the number of points satisfying certain conditions, and he pulled it off. And he really did this, and there is this great theorem, which I can state for you. This is what he was trying to do. So Macaulay wanted to characterize Hilbert functions. He wanted to know when a given function is the Hilbert function of something or is not, under some conditions. And I'll tell you what they are. Wanted to characterize Hilbert functions of graded rings. So here's the answer. But the answer takes a little bit of we have to say a couple of things before we can state what the answer is. So here's a fact. given integers n and k, positive integers, there's a unique expression like this. So you want to write n in the following form. A sub k choose k plus, I'll explain to you how to think about this in a second. I think this is best understood in an example. So I don't know, let's say that n is 7 and k is, it's a good example. Let's say that n is 8 and k is 2. Okay? So you want to write 8 as something, choose 2, plus something, choose 1, plus something, choose 0, or maybe stop somewhere. How do you do it? You look for the biggest something, choose 2 that fits. So what's the biggest something, choose 2 that fits in 8? If you think about it, you'll see that it's 6. 6 is 4, choose 2. It's the biggest guy that fits, and then you need a 2. Okay. But that 2, you have to write it as something, choose 1. And it actually is just 2, choose 1. So this is the unique expression of 8 in this way. So this is a nice fact, and it's not clear, and you should prove it. It's fun. So then, given this, we can define an operator that takes a number and gives you another number. Sorry, delta k of n. What you do is you just shift all of these guys down by 1. Okay. So again, let's just do this in this example to see what this means. Given k and given n, I have to define a number delta 2 of 8. Okay, this is delta k of n. So how do you get this number? First, you write n in this mystery form, and then you take everything that you see and you subtract 1 from it. So delta 2 of 8 is 3 choose 1 plus 1 choose 0. You just subtract 1 from every number that you see there, so you get 4. Okay. So this is some way of something. It's a rule. Given n and k, it produces a number delta k of n for you. So here's the theorem of Macaulay. Given a sequence f0, f1, f2, etc. of natural numbers, we want to know if this could or could not be a Hilbert function. So it turns out that the description is this one. F0 should be 1, and if you know how big fk is, that gives you a restriction on how big fk minus, if you know how big fk minus 1 is, that gives you a restriction on how big fk can be. And that the way that restriction works out is that when you take fk and you apply this lowering operator, you agree that this is a lowering operator. You start with the number n, and there's a kth lowering operator that makes you smaller. This says that if you apply the kth lowering operator. That should be most fk minus 1. So again, the way you should think about this is, if you know what's your degree in, what's your dimension in degree k minus 1, then your dimension in degree k cannot be too big. And how exactly is the rule for how big it can be is this complicated rule. He didn't make it up. I mean, this is just the way it is. That's it. That's the rule. For there to exist a graded ring R, and I'm going to insert some technicalities here, but the point is that this should be a series of R. So what are the technicalities? Technicalities are basically that in degree 0, you should just be the field. In other words, what I want to say is that the only things that get to be degree 0 are the constants. Polynomials really need to have a degree. Polynomials or ring elements. Only the constants get to be of degree 0. Or 0 are the constants. And the other rule is that everything should be generated in the first degree. So what does this say for a polynomial ring? Well, the thing is that in degree 1 you have x, y, and z. And everything higher is generated by x, y, and z. So the point is basically saying, well, at degree 0 you have only your constants, and at degree 1 you have your honest generators, and then you can go crazy and do whatever you want as long as the thing is graded. Then you have a graded ring like this, if and only if C can satisfy this condition.
Is there no restriction on F1?
I'm sorry?
I mean, if
There's no restriction on F1. That's correct. So as soon as you choose F1, there's a restriction on F2, and that gives you a restriction on F3, etc. But F1 you can choose free. Which kind of makes sense, because in degree 1 you can choose generators, and you can choose however many you want. So I think this is pretty amazing, and this is kind of a hint of how the proof works, basically. You reduce it to combinatorics, and then this has to come up from somewhere. So I'm not saying the combinatorics is easy, but the combinatorics reduces to this stuff. So this would be again another very nice project would be to understand all this stuff, and actually there's some really nice extensions and some open problems about this stuff. So